Hello, everyone. My name is Zahari Dichev, and I work at Buoyant, the creators of Linkerd. Today, we're going to do a Linkerd deep dive, and we're going to focus on one particular feature, which is the multi-cluster functionality that was released in Linkerd 2.8. So the agenda for this talk is we're going to look at the what service mesh is and why you might need one. We're going to cover the multi-cluster concepts that governed the implementation of this feature. We're going to look at the general architecture of multi-cluster. Then we're going to do a quick demo showing how this feature feels in the terminal and what you can do with it. And then we're going to look at the life of a request across clusters. So let's get started. A lot has been said about service meshes, and in fact, I think the best way to describe it is through a quote that I read recently on our blog. Naively, you might think that when you have a distributed system, the most important thing is that A and B can exchange packets. And that's true, it is important. However, as your system grows and becomes more complex, you need to be able to provide more guarantees. And what Linkerd gives you is the following. It provides a guarantee that A and B can exchange packets in a way that validates the identity on both sides, has clear authorization semantics, is confidential to third parties, and is measurable and inspectable. So this is a pretty concise quote, but I think it captures the essence of Linkerd, and it goes. And you know, in a typical distributed system, you might have an architecture that looks like this. You have a client that communicates with an API gateway that happens to live in a Kubernetes cluster. This API gateway then routes requests to a number of internal services. And these services might talk to a database or a Redis cache, or for that matter, they might be talking to a third-party API that's reachable over the internet. And this is all great until things start to go sideways. So, for example, your database might become unavailable, or you might deploy a new service version that's significantly slower than your previous one, causing all of your other services to exhibit abnormal behavior. Or somebody might, by mistake, cut the fiber optics cables, and now you don't have connectivity to the internet. And when this happens, or any of these things happen, you want to be able to spot the exact problem, pinpoint it, and react quickly to it. And this is one of the things that Linkerd tries to help you do. And the way we do that is by injecting a proxy into all of your meshed pods. And this proxy, effectively, its purpose is to intercept the traffic that goes in and out of the pod. So instead of your usual traffic pattern, now your traffic looks a bit like this. Everything goes through the proxy. This proxy communicates with a set of components that we collectively refer to as the control plane through interface. And that control plane runs alongside in its separate namespace. So this control plane gives you a few things. It provides TLS certificates for the proxy. So now all of the communication between meshed pods and between proxies is encrypted out of the box. It gives you service discovery utilizing DNS and native Kubernetes primitives. It allows you to configure service profiles. So now you can specify things like retry and timeout rules per service. It supports automatic proxy injection, and it also gives you a web dashboard with a bunch of metrics that allow you to look at the runtime characteristics of your traffic. And it also exports a public API that we use for a number of CLI tools that we ship with Linkerd. The proxy on the other side that we refer to as the data plane is ultralight transparent one written in Rust specifically for Linkerd. and specifically for Kubernetes. And it supports a few things. So it exposes an endpoint that provides you automatic Prometheus metrics for HTTP and TCP traffic. So now your Prometheus instances can scrape this endpoint and give you a bunch of useful traffic information for all the traffic that goes through the proxy. It provides latency-aware layer 7 load balancing, as well as automatic TLS, and an on-demand diagnostic tap API, which purpose is to allow you to look at live requests and the live traffic that's going through your proxy. So it's probably normal to ask, how does that proxy actually end up in your pods? Well, that's done through something that we refer to as injection. And this process is usually accomplished by the proxy injector component, which is part of the control plane, but it can also be done manually. So this actually puts two containers in your pods, an init container and the proxy container. So this is best represented with the diagram. So if you have your usual Kubernetes pod with an application container and some traffic going in and out of the pod, what happens upon injection is that we add an init container. And when that runs, it sets up a bunch of IP tables rules that are responsible for routing traffic to the for making the proxy intercept all the traffic. And we also add the proxy. So now all your incoming traffic goes through the proxy first, and then to the application container. And then similarly, all of your outgoing traffic leaves the application, goes through the proxy, and then to where it's destined. So some of the core concepts of Linkerd are observability, which is collecting actionable traffic metrics, allowing you to pinpoint problems and understand the dynamics of your traffic. Security, encrypting traffic between services automatically. Reliability, as well as traffic management. So you can use advanced patterns like traffic splitting and all sorts of things. And when we were thinking about multi-cluster, we were wondering, how can we have these guarantees and expand them to span across clusters? And first of all, maybe it's worth asking, why multiple clusters? Well, there's a number of use cases, but they mostly come down to traffic migration across clusters. So this includes canary deployments, different environments that allow your developers, for example, to split traffic across a development and production environment and use the production components while developing locally, as well as failover. So a lot of people actually do a failover across clusters in different availability zones and that sort of thing. So we tried to build upon the Linkerd concepts and have our multi-cluster implementation be governed by other core concepts that expand upon the Linkerd ones. So our implementation is secure. Everything happens over TLS, even traffic across clusters. It's Kubernetes first, so remote services appear as Kubernetes services. There's no special kind of service. There is no single point of failure. So no cluster in this cluster mesh is blessed or magical in any way. If a cluster goes down, then that doesn't affect the rest of the clusters. This implementation is transparent, so applications don't need to know whether a service is remote or local. And of course, this implementation is also network independent. So as long as you have connectivity between clusters, then the underlying network hierarchy doesn't actually matter at all. So if we have to look at the architecture of this solution, it looks like this. If we have a cluster east and cluster west, and we're going to look at the demo in a bit, that's going to show this exact situation. These two clusters need to have Linkerd installed. And it's important to know that Linkerd needs to be installed with trust root that with trust root that is shared. So this enables automatic TLS across clusters. And then you have the Linkerd multi-cluster components, which consist of the service mirror, the gateway, and cluster credentials. And then you have your local services that might have pods or other pods behind them. And then you have the remote services that are effectively proxies for services that live on the target cluster. So the service mirror controller is actually responsible for monitoring the exported state of the target cluster and replicating it. This is done through using the client Go and Kubernetes informers in order to continuously monitor the state of the services on the target cluster. Then we have the gateway component, which is responsible, that usually lives on the target cluster and is responsible for routing requests that come in and effectively taking requests on one port and routing them to the correct service, to the correct internal service. And then you have credentials, and these credentials consist of two pieces. So you have the service account that lives on the target cluster, which allows you to monitor, which allows you to inspect services, get lists, and watch services. And you have the secret, Kubernetes secret containing Kubernetes API config. And this lives on the source cluster and is used by the service mirror controller in order to initiate an API connection to the target cluster and be able to spin up the informers. So with all that said, now it's time for demo. So in this demo, we're going to have two clusters, east and west. And each of these clusters has backend service installed. And a test client that lives on cluster east that we're going to use to fire requests. And what we want is to be able to split the traffic to backend service between east and west. So let's actually look at the terminal here. So as I said, you have cluster east that has a backend service and cluster west that has a backend service too. So now what we want to do is we want to install the Linkerd multi-cluster components on both cluster east and cluster west. So now that this is done, we can see that the Linkerd gateway and the service mirror controller is, and they are both running. Well, the gateway is still not running, but same for cluster east. So right now, we want to be able to link these two clusters together. So what we are going to do is that we're going to use the multi-cluster link command to provide credentials to cluster east and allow it to be able to monitor the state of cluster west. And we're going to do that through the Linkerd, through the multi-cluster link command. So now the secret was the secret containing credentials was created in cluster east. The other thing we need to do is to export the backend service from cluster west and make it available on cluster east. And we're going to do that through the export service command. And this export service command pretty much adds some annotations and some metadata to your service YAML and informs the service mirror that this service can be exported. So now that we have that, what we can do is take a look at the services on cluster east again. And now you can see that apart from the local backend service, we have a backend service -west. And this is a service that is effectively just a proxy service, and all the traffic that goes through it is going to be routed to the service in the pods that live on cluster west. So now we can use the gateways command in order to see all the gateways that are available on to cluster east. So you can see that there is a Linkerd gateway for cluster west that is available on cluster east, and there is a one mirrored services. And the latency to this gateway, there are some stats about the latency. So what can we do now? Well, we can use our pod here and in fact be able to hit both services. So we have a response from cluster west, and we have a response from cluster east as well, which is local. Now, the interesting part is that we can actually traffic split between these two services, between these two clusters, right? So we have this traffic split resource here that specifies two leaf services, and the traffic will be equally split between these two. So once we apply it and we get into our pod again, now we can run a curl command that curls backend service. And what's going to happen is that the traffic is going to be split between east and west. And you can see that this is happening because we get different responses. And what's also interesting to observe is that we can actually use the Linkerd CLI to look at our traffic splits and see that our backend service has two leaves, the backend service which is local and the backend service which is on cluster west. And the success rate is 100% for both of them. But what's interesting to observe is that the latency is quite different, right? So it's normal because one of our services is local while the other one is in fact a remote one. So you might wonder, how is that actually happening? So how does that actually work? Well, if we go back to our presentation, yeah, let's actually look at the life of this curl request as it goes across clusters. Well, we have our client pod, right? And this client pod it lives on cluster east and fires HTTP request to backend service that, for the purpose of this request, let's say that this gets traffic split and goes to cluster west. So once that happens, once this request leaves the pod, it's going to backend service west, which is the service proxy that lives on our cluster. Now we do this backend service has an endpoint associated with it that is that specifies the public IP and port of the gateway on cluster west. And because this request goes through the proxy, we can be a bit smarter about what we do with it. So once this request hits the proxy uses the Linkerd destination component, which is part of the control plane, and issues a discovery query to it. Now the Linkerd destination service knows that this is a proxy service, so it's going to return some useful information, namely that's the fully qualified domain name of the service on the target cluster, because it might be different. You might have different cluster domains, for example. So when that happens, it's also going to return you the expected identity that for the gateway. So you need to hit the gateway endpoint on the other side with the right TLS identity in order to establish mTLS. So once that happens, this requests the URI, the proxy rewrites the URI authority with the correct port and fully qualified domain name. And when this request leaves the pod or the cluster, in fact, it hits the external IP of the gateway on the other cluster, on cluster west. And this gateway now knows which port, because the URI authority is rewritten, this gateway knows which port and which service this request is destined for. So it sends it there, it routes it to the correct service. And it's important to understand that, because there are proxies running in each pod that's involved in this communication pattern. All of this traffic is encrypted, even traffic that's going across the clusters. So this is how it pretty much works under the hood. And some of the future work that we're planning to do on this particular feature is that we've realized that the service mirror controller, because it can monitor multiple clusters, can get a bit complicated. So what we decided to do is to split this controller and have one controller per target cluster. And hopefully that makes things a bit easier for debugging and reduces the cognitive luggage that one needs to carry when dealing with multiple clusters. We are also going to introduce a CRD to better represent the target cluster information, because currently it's represented through a bunch of annotations on both services and Kubernetes secrets. Now we're going to consolidate that and use a CRD. We are also going to support traffic policy and finer grained permission control. And one thing that we are currently working on is support for TCP traffic. So currently that solution works with HTTP traffic, and we want to be able to support just arbitrary TCP traffic. So that's part of a bigger pile of work that we are currently focusing on, but we have a clear idea of how that's going to be accomplished. So it's just a matter of time. So with all that being said, now there is some time for Q&A. There is also a link here that to a GitHub repo where you can find this talk, the slides for this talk, with all the resources that you can use in order to experiment with all of that yourself. So hi there, I'm happy to answer any questions.
Yeah, hey Zahari, you can take a look at the Q&A zone in Zoom, and then just pick up whatever questions you want. Thanks.
Yeah, sure. So the first question is does multi-cluster support gRPC? And yes, it does. It does support gRPC, so you can use gRPC across clusters.
We have 3 questions right now. Can you see them all, or?
I can see 2 questions.
Oh, okay.
So,
yeah, just go ahead. Yeah.
So yeah, the other question is, ISTO has been very popular. How did others typically choose to use Linkerd instead of ISTO? Well, I'm not particularly, yeah, I don't really know why other people were considering Linkerd instead of ISTO, or how they are using it differently, because yeah, I don't really directly work with a lot of people, but I would say Linkerd is quite simple in its UX, and getting things off the ground is really simple. So maybe that's something that is kind of attracting people. So yeah, there's another question that the data plane of Linkerd is written in Rust with all the benefits of it, but could this be a reason that people who don't have internal Rust developers avoid Linkerd? I don't think that this could actually be a reason because, or rather, I don't think it should be a reason because the proxy is fairly transparent. So, and because Linkerd is like very configuration light, you don't really need to know a lot about the internal workings of the proxy or or Rust for that matter in order to be using Linkerd to its full potential. So yeah, I don't think that should be a decisive factor. If we update Linkerd version in multi-cluster, will it cause any downtime to current workload? No, I don't think it should. Technically, I don't think it should. It's all about, it's all about service proxies. So the upgrade path at the moment is something that we are actively working on because there are some other changes that we are incorporating in the Linkerd multi-cluster solution. But I think at the end of the day, it should be quite smooth. What's the most advantage for Linkerd compared to ISTO? I don't think I have the user experience to answer that question, and I think that could be different for different users. So, like I can't really comment on that.
Okay. Really great talk from Zahari. Thank you.
Thank you.
Yeah,
Thanks
thank
for
you.
having me.